Okay, hey everybody. Welcome to what will be the last installment for this year of tutorials, although there is one more on the GitHub page, which I'll just show you real quick. It's going to be the same data set. It's going to be comparing what I'll show you to a slightly different way to model binary outcome data. And so that'll be discussed, over the next week or two. But I won't do a tutorial for that one, as it's just kind of a comparison of two ways to do this. So um, when we switch to non-continuous data within multi-level modeling, things get a little bit more complex. For illustration, we will actually use the data that you're able to use for your project, and we will use one of the outcomes that you're allowed to use, but it shouldn't spoil it for anybody because you can clearly, definitely do more stuff on that. So, talked a little bit about that. You've heard this from Dr. Wallace, that there are there are a lot of different zip codes in the Southeast Pennsylvania area. And for the purposes of modeling, it's a little bit more stable to use zip region as a clustering variable. So that's what we're going to use today. So it's basically just a few adjacent zip codes were merged, that made a little bit more sense. And there's just a greater number of people in each of the zip regions compared to zip codes. And that's going to be important for today because it's going to make the proportion of folks within each cluster having an outcome a little bit more stable. So what we're going to use, for example, of an outcome is the incidence of emergency department visits in the last year reported by respondents in this survey. So there's some really nice stuff in, so I'm going to adapt kind of the coverage of this from book by Snyders and Bosker, as well as from the book by that you've been using. So you can kind of ignore this. Is basically tabulating the number of people who had an emergency department visit by zip region and performing a chi-square test, goodness of fit on that, which is basically the null hypothesis would be that the number or proportion of people with ED visits is constant across zip region, which of course will probably be false on the face of it. This test, which has a very small p-value, it says no, reject that idea. Not, and again, probably shouldn't be surprised by the fact that the proportion of people who go to the ED does vary substantially across zip codes. So what we want to do is we want to model that variation and take it into account in modeling individual predictors of hospitalization. So kind of a cool thing that we can do is to sort of try to visualize what the model is going to be doing. So first off, so from this table, if you make this table, we can use it to get some descriptive statistics that are going to influence or kind of help us with our modeling. So the first thing we're going to do is overall, right? If we ignore where people live, 27.19% of the respondents of the survey said that they had been to the emergency department at least once in the past year. Now, if we then go ahead and per zip code turn the counts into proportions and plot them, we get something that looks like this. So this is a density plot, which is a smooth histogram, right? So instead of a histogram, we see what is an estimate of the probability density, the probability distribution of these proportions. You can see that it's actually sort of roughly normally distributed, and that will happen for when you have binomial data and you group it into a large number of groups, if the event is not too rare, often you'll get a somewhat of a symmetrical distribution. That's important because we're going to see this in a little bit, that just like in other random effects models, we want the sort of cluster variation to obey certain assumptions, and this is one that's going to help us out. So again, we can see there's some variability. The average is around here. There's a little bit of a skew. So this is important, right? So in order to properly, in my view and most statisticians' view, properly kind of disentangle what's going on here, why do people utilize the emergency department, it's a good idea to differentiate between the sort of contextual effect, which is, on average, different zip code regions have different rates of hospitalization or ED utilization. So that's kind of one piece of the data generating process. So if you select a zip code at random or a zip region, you're likely to have some, the people from that zip code to sort of automatically be more likely to go to the ED versus some would be less likely, right? That's a pure hierarchical model right there, that there is a probability distribution over the zip codes in terms of the proportion of people, or I guess the probability of utilizing ED. And then within each zip code, people will also differ. And so that's what we're going to do, and that's how it's been done so far. But when we change from an ordinary linear model to a generalized linear model with a length function, basically what happens is the interpretation changes a little bit, and some of the estimation comes a little more complicated. Okay, so let's just start by looking at the unconditional model. Because this is essentially logistic regression, we are trying to model the linear part of the model is the logit function, if you remember. So logit is the log of the odds of the event. So we write it this way, logit P. So basically logit of the probability, which really we can translate to odds. And we see that in the unconditional model, we allow each zip region J to have its own log odds for its residents. And then since it's unconditional at level 2, again, we just account for that variation. Note that we don't have the usual level 1 random effect explicitly here. It's dealt with in the estimation process, but it's not going to be reported in the same way, and that's a consequence of it being a generalized linear model, because the error now is not a normally distributed variable. It's, in this case, the error is binomial, because that's what the outcome is. And so what the results of this model will do, just like as normal, is it's going to give us a look at the variation in the logits across our clusters. So in this case, variation in the log odds of ED utilization across clusters. And then it allows us to kind of, see, because sometimes, and this is very true in these types of models, sometimes there is not a huge level of variation in the logits. Mainly because they're kind of, logits aren't constrained, but probabilities are constrained. And if the outcome's very rare, then it might be that, there's a few clusters with a small probability and everything else is 0. And essentially you're going to have a model with very little level 2 variation. I chose this variable on purpose because it has a little bit more. So the fitting process is almost identical. It's kind of like merging the GLM function that you use for ordinary modeling with LME4. So there is a glmer, which some people call glmer. You can call it whatever you want. It's a function in the LME4 package. It's based on GLM, as we learned before we got into mixed effects models. And so the syntax is the same as regular LMER, regular Elmer, right? If we look down here, we still do the outcome. In an unconditional model, we only have random intercept, right? So no fixed effects. This is the same notation. We still call out a data set. And just as before, when you use GLM to fit ordinary logistic models, we use the family equals binomial argument to get, again, to, I don't actually have to walk my dog today, if anybody saw that, so that's good. So we have to make sure we do this to model those level 1 errors correctly. And of course, when we do that, we turn it into a logistic model. You'll notice that there is no REML argument here because there is no restricted maximum likelihood estimation in this case. All estimation is done using the normal likelihood, and there's two ways to do it. I have some info on it next week that's optional. Basically, what happens here is there's like a double-edged sword. Because this is a generalized linear model, we can use maximum likelihood estimation. The problem is well posed. The issue is that the equations just become a little bit more difficult to solve when we have random effects. So there have been two ways to do that. There's more than that, but the two that are used in this in the LME4 package are Laplace approximation and Gaussian quadrature, and they're just two different ways to approximate the integral that needs to be computed, and essentially the quadrature, which is more complex, can be more accurate but takes a lot more time to run. This is true in general. GLMER is limited in the sense that with very large data sets and a large number of clusters, this function can sometimes take a long time to run. There has been a new development in the past few years, a new package, GLMMTMB, which I won't go through here, but I gave you some info about it in the overview of the project. It works exactly the same, but basically it was designed to speed things up a bit through some tricks in computational statistics. So you won't have to worry about that. We're always fitting with maximum likelihood. Because of the way that the errors are modeled, you're only going to get, and we'll see here, you won't see residual error anymore. We'll just get errors for the random effects of various clusters, and we only have one, so we have our zip region error there. And then you will get p-values here. They're based on walled tests, and sometimes they're not correct, but they're generally okay. Again, based on normal theory, the coefficients, as you can see, there's no degrees of freedom because this is a z test, so that's a consequence of maximum likelihood estimation. There still can be some problems in comparing models with a likelihood ratio test and with these p-values. So again, confidence intervals are a little bit safer, but those are the main differences. So just as before, we have an estimate of variance, again, in the logit across zip regions, right? So this is giving us variance and standard deviation in the log odds of an EV visit across region. The intercept in this model gives us the logit for the logit for the sort of the overall mean. Now here's where we have an issue, right? So first, let's turn this logit into a probability, right? So the model estimated mean logit ED visits is negative 1.02, which is doesn't help us out very much, right? So we can use the logistic transformation to turn that into a probability, right? So by raising e to that power and computing this little equation, the model-based estimate of the probability of ED utilization without knowing anything else except for the zip code is just a little bit smaller, right? So this is a shrinkage estimator, meaning we've shrunken sort of a little bit more towards zero here. This is a consequence of what's happening with these models. And so the other thing we have to understand is that this is true in the other ones, and you'll have a reading over the next week about this. Any model with random effects like this, the estimates are cluster specific. So this is basically telling us the typical cluster, one with a random effect of 0, essentially that's just an average. At this point, we don't know anything else about the clusters. So we can just say an average cluster. We'd expect an ED visit to occur within that cluster with a probability of about 2.65, right, or 0.265. Or you might think of that, in a typical zip region in this area, either about 26.5% of the residents would need to go to the emergency department, or you could think of it as a probability. Now, the variance of the intercepts, which is not the standard error, but here, the variance, we can turn it into a standard deviation and again estimate sort of the distribution of the logits, not the probability, right? And so there's some really nice code that can kind of help us visualize that. And so I won't step through this. Basically, what we're trying to do is create some numbers that will help us with the curve that we're going to draw, and then we're going to actually plot the logits on the bottom of the plot, right? So our model is telling us that the distribution of random effects, right? So the distribution of logits should be centered around that negative 1.02. And, so again, we have some high probability, low probability. It's not exactly symmetrical. So what we're checking for here is whether these cluster random effects are normally distributed. This isn't exactly what we're looking at. These are our observed logits. This is a normal distribution that I've drawn based on the model. Right? That's what this part is. Taking things from the model, turning them into something that can be used to plot normal distributions. So if you're interested, you can take a look at the code and the Snyders and Bosker's book about sort of what's going on here. So again, this is giving us the same information as before, now seeing it as a model-based estimate that, across these 30 some odd zip regions, there is quite a lot of variability across them in terms of ED utilization. Right? That's all the unconditional model is doing for us. It's just giving us a sense of, again, parsing out this variability across clusters versus within clusters. And that's setting up. So in this case, because the variability is wide, there's probably some things at the zip region level that we can use to try to explain the variability or get rid of it in some way. Other times you might just be focusing on person-specific stuff and you want to just adjust for the fact that two people in the same cluster would have similar log odds compared to two people in different clusters. So all we're going to do here is just add some predictors at level 1. This is kind of makes this, you'll find if you run this model This will take a little bit of time to return. So don't freak out. It's because essentially we're approximating a likelihood function that's very complex, and then it's an integral that needs to be basically marked. It's daunting. So it takes a little bit of time even for a modern computer. So here we're just going to try to model a person's log odds of an ED visit based on their sex, age, BMI, race, and an indicator for their level of poverty. So we do that, and as usual, we get information. Now, interestingly, this doesn't always happen. Usually we have variance shrinking at the cluster level when we have cluster predictors, but here we have only person level predictors. But we've somehow explained some of the variation in zip region, probably because poverty levels are a function of the neighborhood you live in, not your personal income. So we do indeed have kind of a quasi cluster level predictor in this model, which, as you can see, has a very small p-value, which a lot of these p-values will be small in this data set because it's a big data set. So we'll be interested in looking at odds ratios. So none of this is different from before. They're all categorical variables. So we're going to have these contrasts. So female compared to male, which is missing, right? That's the comparison group, reference group. The reference group for age is the lowest category of age. BMI is numeric, so we leave it as it is. I use the scale function because it's a very good idea for stability and also for interpretability that numeric variables, as we've talked about before, are centered in multi-level models, and that doesn't change whether we're using a generalized linear model or ordinary linear model. So again, these coefficients are telling us the direction of the effects, but they're on the log odds scale. So we can kind of roughly get a sense of, for example, as BMI increases, for each unit increase in BMI, the log odds, logit of an ED visit goes up by 0.123. Similarly, compared to those who are in poverty, if you're not in poverty, your log odds of an ED visit go down by about 0.56 of a logit. Again, logit's not super intuitive to think about, so we often use odds ratios. Note that if we're interested, so we'll get to the odds ratios in a minute. If you're interested, you can run this model where we're using Gaussian quadrature. It takes a little bit more time, about 2 seconds to run. Ostensibly it should be a little bit more accurate, but as a good example, we can actually see, so here is the model we just looked at, model using a more precise way to estimate, are almost identical. So in fact, there's a lot of times, unless your model is really poorly behaved, you can get away with, so note that there's no additional argument here. If we leave off this, you see it here, if we leave off this NAGQ, right, which is basically how much number of adaptive Gaussian quadrature points, which is, I've set it to 10 here, which is a decent amount. If we leave that off, then the default is to not use quadrature, to use the Laplace approximation, as it says here. And so I'm just showing you that for all intents and purposes, it probably doesn't matter what you use. If you want to get fancy, you can use quadrature. If you increase the number of nodes greater than 10, it's going to take a really, really long time to run. And this is kind of telling us that we may not really get any better estimates. So there it is. Similarly, the random effect estimate from the two different estimation procedures is almost identical as well. It only starts to be off in the thousandth place. So this is just a way to say that there are a few subtle differences between fitting a model with glmer versus lmer, but you'll get very similar outputs that's very, very similar to glm output. And then you'll only see the random effects for the clustering variables that you put in to the model. You won't see the residual variance anymore. All right, final thing, and this is kind of the big one, right? So here's the same results again, reproduced in a nicer looking table on the log odds scale. The main issue with multi-level logistic regression models is that when we exponentiate these numbers, so when we do e to the negative, well, not for the intercept, but we do e to the negative or e to the positive 0.12 to get an odds ratio for BMI, then we really need to respect the cluster specific piece, right? So this is a nonlinear transformation, and so because of the nonlinearity, it becomes important to qualify these as cluster specific. So we can again get confidence intervals in the usual way by exponentiating the ones that come from the ordinary model. So again, let's pick out BMI. Okay. So we have an odds ratio for BMI of a 1.13, which is essentially a 13% increase in the odds of hospitalization as BMI goes up by 1 unit. Similarly, for females compared to males, we've got about a 12% greater odds of ED utilization if you're a female compared to a male. That's all the same as before. We have to qualify this though, right? Because usually we will say, when we're being more, careful, that when we interpret results from multiple regression, that really we're saying such and such has this effect, but while we're holding all the other variables constant at some level, and we're assuming that there's no interaction between variables, such that it doesn't matter whether we think whether we're talking about males or females when we interpret the BMI effect, right? If there's no interaction in the model, it doesn't matter. If there is one, if we think there is one, then we have to add it, and that's a whole new set of complex issues that we're gonna avoid for right now. Because of that, right, we are implicitly also holding the cluster constant too, right? And that's true in the other models as well, but it doesn't have the same impact on our inference as it does here, right? So the nonlinearity induced by changing to odds ratios means that different clusters might have very different odds or very different probabilities attached to them. And so there's some extra things that we have to do to kind of make sure that our cluster specific estimates actually cover everybody else. If you're not interested in cluster specific stuff, then you want to go with the so-called population average model, which is the topic of next week. There's a great overview of this on the UCLA site. It's all the way down the end. It's a little bit, there's a lot going on here, but I think it's worth it to read. But I want to demonstrate to you what this is all about, right? So here are the predicted probabilities of an ED visit for anyone in the 25th percentile of random effects. So what I did here is I held within the model, within the data set, I said we're going to take only people essentially from one cluster. This cluster happens to be a random effect of negative 0.058. So this is, folks, remember the average from the unconditional model. Actually, so this is a conditional model. So the conditional estimate of the log odds is a little bit higher in this model because of the reference groups. Anyway, these are folks who have a slightly less, this cluster, ignoring the other stuff about the people, has a slightly reduced log odds of ED visits. Here are the predicted probabilities from the model, which are done exactly the way you would do an ordinary regression. You just slot in for each person in this cluster. We put in their predictions, or put in their all of their values of the covariates, and then we produced predicted probabilities from the logits. And here's what they would look like if they all came from one cluster, right? With this random effect. Okay. Again, as before, right? Most folks have that 25% chance, with some up the top sort of skewed there, but most people are down low. What we want to do is, so one thing you can do to see if your cluster specific effects really are cluster specific, or whether the model does kind of work all the way up the risk scale, is to look at different parts of the random effect distribution. So again, this is us predicting probability of hospitalization or ED visit for everyone in our data set, pretending that they all came from a cluster with this random effect, right? Which would be on the low side. If instead we made everybody come from the 75th percentile, which is a random effect, which is slightly positive, which means that in general this cluster is going to have a higher propensity for ED utilization, we actually don't see that much of a difference. And in fact, the average predicted probability is 0.23 in this lower random effect situation, and is only a little bit higher in this big one. So the distributions aren't that different, right? This is median predicted probability. So in this case, there may actually not be too much variability across clusters, as such that these odds ratios actually do apply across the board. But we always just want to make that final qualification that what we are actually doing is we're modeling these effects within clusters, and then if we have anything at the cluster level, between clusters. Now, because we do have some between cluster information in this model about poverty, that may be the reason why we don't have this huge shift in the random effects, because again, if we look at the residual variance in this model, not the residual variance, the conditional variance of the random effects, they're actually much smaller, about cut in about half compared to the other model with no predictors. Okay. So that's it for this week. Again, just really the basics of glmer are pretty simple. The tricky part is just getting this down, practicing these cluster specific interpretations. And again, I really do urge you to take a look at how it's described here. A similar example, if you scroll down, is done for you where things do change quite a bit. So if you look at the interpretation part of this example, you will see that with this particular example, as the random effect changes, we can see how the distribution of probabilities change substantially in this data set. So urge you to take a look at that, and next week you'll have more time to practice it. All right. Hope that helped, and please get in touch if you have any questions.